Hello. Hi guys, good morning. Welcome back to the new video, and it's a complete backtracking guide for you for sure. After this, any question of backtracking you should be able to solve. You will see many questions. Firstly, a basic structure of backtracking. We will see subsets. We will see another problem, subsets 2. We will see combinations. We will see permutations. We will see permutations 2 as well. Like we gonna see every major problem of backtracking so as to get the idea. It's combinations. Next is combination sum. Next is combination sum 2. And not only this, but also like we will see, okay, what are the major problems for backtracking, and like what are the problems not of backtracking and of simple recursion, which we get confused of. We'll also see that, and also we'll have a quick question for the practice. These are questions for your practice, and ultimately for sure one of the hard questions. Let's have a look at that as well. So yeah, that's gonna be a big video, but for sure that will be a complete backtracking guide for you. Cool. Starting off with the first itself. Okay, how the backtracking works. Cool. You will have a simply start point. When I say a start point, I mean, okay, it may be starting from some index. It is usually index 0. When I say index 0, it will start from that index, and moving forward, we will actually build the answer with that. When I say index, it can be an integer array, it can be a string, it can be an array of string as well, right? So that will be a start point for us. Now, as we have a start point, we know we have some possibilities to add after that. Okay, I can have the start point as anything, right? I can, let's say my string is ABC, so my start point can be A, start point can be B, start point can be C as well. So after, let's say I have a start point as A, then still there are multiple possibilities remaining after the start point. So I will just go on for all the possibilities. Now for each possibilities from the start point, I just check if that possibility is actually safe or not. When we say safe, we actually mean that we are checking. It is not that, okay, we will just do a simple and bring out everything. It can be possible that the question is saying, please put a condition that, okay, it should be a valid answer. So before actually, okay, we have a start point, we are actually going on and trying multiple possibilities. But as we try on any possibility, we have to go and have a look, okay, if that possibility is actually what the answer want us to deliver or not. If that is the case, you can simply go and choose that possibility and then make a recursive call to rest of the possibilities. But make sure that, okay, when you have made the recursive call, which means after choosing this possibility, you also give the chance to other possibilities to be chosen rather than this possibility. What I mean by that is, let's say your start point was A. You choose a possibility, and as I spoke, okay, I have a possibilities as ABC, right? I have a string, let's say. Now I'm saying, okay, my start point was A. Let's say now I am choosing another possibility as B. So I'll go and find every possibilities for that path after B. But it is also possible that I will choose, rather than B, I'll choose a C. So basically, earlier I choose a B, but then I have to remove it, or basically make it taken as false and then choose C instead of B. Okay, now after the start point, another possibility for me to choose is this C. So that's the reason we just selected any possibility which we encounter, we selected. And please make sure that, okay, it is safe to select that possibility, and then we just make a recursive call. And then we, after making the recursive call, which means after finding all the possibilities for this selected item, I just deselect that item, which means I'll replace that item with another item. So I have to remove that item from it. I have to remove the item B from here, so that now another possibility, let's say C, can come in picture. And that's how the major function of backtracking works. That, okay, I have to undo this move of which I did a selection. And for sure, if the step is not safe or the path is not safe, so please continue, you don't go on that path. Now we'll actually, okay, it's a basic rough structure you will see in the code of every backtracking problem. Now going on to see, firstly, you know that I know that, okay, recursion is very important. If you have not known recursion, or if you are just still confused on recursion part, or if your recursion is not strong, you can't think of recursion, so I'll highly recommend go and watch the recursion complete intuition playlist, and also the AP Complete Intuition playlist. In that, we have taught recursion in complete detail. Now, coming back to backtracking. Cool. First problem, very standard, asked in Google, Amazon, Facebook. Great. Given an integer array nums is given of unique elements. Please make sure it's unique elements, right? Return all the possibilities of subsets, which means I have to return for this nums all the subsets, and the solution must not contain duplicate subsets. When I say duplicate subsets, I mean if I have a 1 2 as one subset, so 2 1 is also the same subset. It's just that okay, it is ordered, right? So I just want okay that everything should be unique and everything should be occurring once only. Return the solution in any order, which means I have to go and find all the subsets of nums, right? For sure, it's a brute force thing, but now comes it okay to go and try on every subset, which means let's say if I have, and again going back to the basic example, I have 1 2 3. Let's say if I have chosen 1, so one is subset and I want to choose let's say another element, so one subset can be 2, but it can be possible that if I have chosen 1, another subset can be a 3. So basically, so I choose an element, then I would be going and further choosing other elements. Let's say I choose a 1 2 3 after it, let's say, right? Or it can be either 1 2 itself. That's a good subset, which means it's also one subset, it's also one subset. But after choosing 1, I have to remove, sorry, after choosing 2, I have to remove 2 and choose a 3. So that is how we know, okay, backtracking part will come in picture. Now, standardly, we know we will have a start point. I will start from the index. I'll go and choose a next element, and there is no condition whatsoever, so I can simply go and choose. Although the condition here is okay, you should not take duplicate subsets, but what I will do is I will take indexing. One ways, or either you can just simply sort in the beginning, but that's not required because okay, if you just want not to take the duplicates, which means if I have to choose a 1, then I will try and start choosing from 2 itself. Okay, I will choose a 2, then I'll start choosing from 3 itself, which means as I have to maintain, okay, I know I will be choosing a start index, okay, it's my start. I have to also make sure that I am keeping track of the index which I am choosing, because if I know, okay, right now I have chosen, I had started previously from 1, which means location 1, which means I had already chosen 1. So for sure, if you don't want to choose that again, so please next iteration start from next index. So that is how we can maintain the okay, I am not taking the duplicate elements, because it can happen, okay, let's say I choose 2, but if I'm starting back again from this 1, which means starting from the very start, then I will be choosing 2 and then again a 1. So that can be a duplicate counting. So that's what we not require. So we will just simply move on ahead. That's simply. And for sure, it's a backtracking stuff. So we will just simply choose it down. We will simply call a recursive function and see. Please make sure that, okay, how to visualize recursion. Although I can make the entire recursive tree, and that we have done in the entire recursion intuition playlist, and also the AP intuition building playlist. We have made the entire recursive tree very big. But here we have to understand that the beauty of recursion is that just assume it will get the work done. Just think of the small part and assume that okay, the rest of the part, the recursion will get you done, and the remaining you can just bring in the answer. Let's quickly see the code. See, that's the reason I just specifically mentioned, just grabbing a basic idea of recursion. Okay, what's the recursion is. Now coming back to how we can use recursion, and then just adding a slight functionality of backtracking so as to get all the possibilities out. Cool. Simple stuff. That list is my final list as my answer, and for sure the folks are watching for the permutation part, which is the actual question of today's, then simply go and have a look at that. But yeah, that's the reason I'm just starting building for every problem. We will actually build, okay, how actually it is being thought, what actually we want, what actually we don't, and all that stuff. Cool. This list is actually the final list which we need to return. This temp list is the temporary list which we are making at every point of time, which means that okay, user saw I have a 1. You saw after that I can add a 2, and after as we do backtracking, which means I'll remove a 2 and I will add a 3 instead, right? Here after 2 I can add a 3. So basically, as you know, I'm adding a 3 after 1. a 2 is added. So now the list has become a 1, 2. Here after 1, a 3 is added. So now the list has become a 1, 3. Here after this, I will simply add a 2, which means, sorry, add a 3. So it will become a 1, 2, 3 as a list. So that is how I'm simply adding in my temporary list which I'm making, and this I can just, okay, it is one list form, so I'll simply push this in my final list, which is the list. So at every point of time I need the existing temporary list as well, so that's the reason I'm just taking this temporary list with me. Now for sure, here you have written sorting. Is it required? No, it is not. Because why? As we saw, to just counter this stuff that you should not repeat it, you might think, okay, I should sort it down. But simply, even after sorting it down, if you start again back from very start, you need to maintain, oh, have I taken it or not? So for now, just assume it is not required, and actually it is not required. You're not required to sort it down anyhow, because ultimately you are not concerned about any duplicates in the entire array. Why? Because you know there are unique elements. There are unique elements, which means the elements will not repeat at all, which means it will not have a 1, 2, 2, 3. It is not that, okay, you would be requiring to take only this 2, only this 3. It is that, okay, there are unique elements, so you will be taking only 1, 2. So for sure, okay, 1, 2 to take. The only condition is that, okay, if you take an index from here, next time please make sure that, okay, you do a I plus 1, right? So that's how you can simply maintain it. So sorting is not required because the elements are unique here. Mark my words. Cool. Now I will just simply call the backtrack function, which is a simple recursive function, passing my main final list, passing my temporary list, which is right now empty, passing my nums, which is the input, and for sure, as I showed you, I need to pass the starting index because I need to pass the start point from where I'm starting out. Now coming back, okay, ultimately my list will have the final answer of all such subsets, which it will return. Now coming back to the actual function of backtrack, which is a simple recursive function. Firstly, as you saw, I need to push in all. There's no condition at all. I need to, whatsoever temporary list I am forming, I need to push that temporary list right now. So I'll just simply, in the starting itself, I need to push all the temporary list in my list for sure, because it is what I'm doing, and that is okay. Simply a first return condition, because for sure, as your answer is being built, you need to push that in your final list, right? So in the beginning, you will see that, okay, your temporary list is being assigned to the main list as you're building your answer, right? Now coming back to the actual function, as I showed you, just simply go on in the start itself. Now you know that you will try for every possibility, and see, whenever to write the recursive, that's the reason I'm not building the entire tree, because it is very hard to go and every point build the entire tree itself. Just go at the midpoint. Just imagine that you have a 1. Now you know, okay, your start index is from 2 itself. Your start is from 2 itself, and you know the end is up till 3. So you know, okay, the input was 1, 2, and 3 array. 1, let's say you have already taken your start as, let's say, from 2, index 2, which is the, let's say, when I say index 2, I actually mean the index 1. So it's actually, indexing is real time is 0 based, but here let's say we take it to 1 based. So when I say index 2, so for sure, you know, I will try to put in the 2 itself. Now if I try to put in a 2, so 1, 2 is already one thing is made. So I will just try on for next possibilities. Now here you will see I start from the index, start index, and please, every time in recursion, please make sure that you start from the mid. Take any small mid, which means you saw, I assume that I have a 1. Now I assumed, okay, I'm starting from 2 itself. That's very much required for interviews, to actually think in interviews, because of new problem, because it's a standard problem. But yeah, what if the new problem comes in contest or basically interviews, so you will be able to solve it. Coming back to, okay, I assumed, okay, I have a 1. Now my starting was pointing to actually a 2, so I have to add a 2. So basically what I did was, in my temporary list I was having a 1, right? So in my temporary list I pushed a new element, which is nums of I, which is starting from start and will go up till end, right? So I pushed in this number element, and then for the next, which means I plus 1, because it is the I right now, my I is moving from start to basically nums dot size minus 1, right? So my I is moving from here to here. Now right now at this, my I is here. So now, okay, I have taken a 2 in my temporary list. I will go and ask, just bring me recursion, just bring me all the possibilities starting from I plus 1, and I will just push in my temporary thing. right? So that is the reason my recursion will go and bring this I plus 1 for me. So I just say, okay, right now element 2 I pushed in my temporary list, which is having only 1. Then I just ask my recursion, go and take this temporary list 1 2 with you, go and take this temporary list 1 2 with you, and go and find all the possible subsets starting with I plus 1. Cool. Now this will go and find all the possible subsets starting with I plus 1, taking the temporary list as 1 2. But I know I started with only 1. 2 was just another possibility to add after 1. What if I want to add a 1 3 and take all the possibilities? Which means, let's say I had a 1 2 3 4 5. So 1 2 I take as starting, and then I was trying for rest possibilities after 1 3 5, like 1 2, and then let's say 1 2 3 1 2 4 1 2 5, and so on and so forth. But what if I just want 1 3 4 1 3 5 1 3 4 5? So I want something like this, right? So I just want to remove 2. So what I will do is, I know in my temporary list I have pushed in a 2. So please remove it back. In my temporary list, I just pop it back. Which means I pushed in 2. I know, okay, now I need to try for the next element. Which means I will move on. As we know, I will move from start to nums of size minus 1. So I is here right now. Next time I will move here. But I just want, okay, my temporary list earlier was 1. I was trying on for every I. Right, pushing in every I, nums of I, and for that nums of I, my recursion will bring in the rest of the answer. So coming back, 2 is taken. Now, okay, remove 2 so that next time 3 can come. So you will remove 2 here, last element which you pushed in, last element, you just removed it back, and then as the loop will go on, it will just have the next I, push in the next I, try on all the possibilities after the next I, and then pop it the next I back. And then again it will just simply go on and try for every possibility. Which means this for loop, what it will do is, okay, if I have the input as 1 2 3 4 and 5, and let's say my temporary list has 1 right now, so this for loop will try on, and let's say my start is from here and end is, let's say, here, right? So this for loop, what it will do is, it will try for 1 2 1 3 1 4 1 5, and this recursion will be bringing for the rest of the part. And that's how you just actually think of the recursive problems. And that's how you saw the basic structure is still followed. You just did an operation, and for sure you saw, okay, Aryan, you told about the if condition, if it is safe path or not. I will say, oh, you have to bring in all the paths, so every path is a safe path, so no if condition is here right now. But yeah, I just pushed in the element. I just asked my recursive function, please bro, bring in all the possibilities after I plus 1, and I assume that he will bring me the answer. Provided when I am returning back, which means, okay, all the possibilities are found, everything is done, it returned back. Please, when you return back, please remove this so that I can add a 3 after my 1, because I am ultimately adding in my temp list only. So that's how you can that's simply a so short and simple code to get all the subsets. Now coming back to the next question, for sure the PDF will be down below for your code reference. But yeah, going on to the next question, which is subset sum 2. The only difference between the two questions is that here you have an integer array nums which may also contain duplicates, which means you might be having duplicates. Which means if I have a subset as 1 2, so let's say I name it as 1 small 2 big 2, right? So basically 1 small 2 and 1 big 2 both are same. So you have to make sure that while I have this, as we saw above code, we will look at the same code, exactly same code. It's just that I know, okay, I will choose a 1 in my temporary list. Now let's say my start is here, now let's say my end is here, or let's say my end is, let's say, 3. Any way you can, and every time I will show you the mid part, which means I assumed 1 has started, I assume I am at the mid of the location, I assume my recursion will bring me the answer. Then how I will make my recursive condition? Cool. As I know I will have a 1, so big thing, if you choose a 2, which means if you choose a small 2, now earlier what you were doing is you were popping it back and then pushing in the next I element, right? That's what you were doing. But please make sure, as these two are same, so please, if you have pushed in and the previous element was also the same as that of this element, please don't push it now. please don't push it now. Which means I was starting from here. It is my I. Okay, I just simply push it down. Cool. 2 is pushing. Now my I is here. Oh, my I is here. And this nums of I and this nums of I both are same. Oh, both are same. So basically I cannot push it. So that is the condition. Okay, it is a valid path. So I will not just push it. I'll just simply do continue. As this 1, 2 is gonna come, I know, okay, this big 2 was equal to the small 2, which means both are 2s. So I'll just not push it, which means I'll just simply continue here. And then my I will move here. So I will just now have 1, 3. Now you will know, Aryan, you just here showed that, okay, you are saying this this big 2, you are comparing with the previous small 2. But what if I say, okay, the 2 is right here? Then how would you know that 2 has occurred or not? Ooh, that's a good question. So for that, what you can do is maybe you can take a hash set, or maybe an unordered map, or maybe a unordered set. Or what you can do is maybe you can take a visited simple array. If you know, okay, the numbers are not in that range, so you can take a visited array kind of stuff. Or maybe what you can do is I'm just showing you multiple hacks to just solve the same problem, because your ultimate task is just to make sure, okay, you are not taking the same stuff again and again. Or other task is that you can simply sort this entire stuff down so that every same element will come adjacent to each other. So this big 2 will come in close to small 2. So if I've taken the first 2, so afterwards I will just make sure I am not taking that previous 2. Which means if I've taken this particular 2 with this one, which means now with this one for the next 2, which means here I saw for this next with this one, the next 2, small 2 I took. For the big 2, I will make sure, okay, I'll just go and compare if it is same with the previous element. Oh, which means it is a duplicate. If it is same, please don't grab it at all here. So what I can do is I can just simply sort it down and will compare with the previous element to know about the duplicates. That is how you can simply solve it. Or if you don't want, you can simply use a hash set, unordered map, unordered set, anything whatsoever you want, just to know, okay, you have encountered that element or not. But that code might get a bit tricky. So rather, because it is not that, okay, if I've taken a 2, I cannot take another 2. It is just that, okay, after in this attempt, if I've taken a 2, I cannot take next 2, which means I have taken 1, 2, 2. So again a 2 can come, and then a 3 can come, or maybe a simply 2 and then 1 small 2 big 2 3. So that is how you know, okay, 2 can come when, okay, it is the temp, right? But what if it is not a temp? If you are building like this 1 2 3, 1 big 2 3, then it is not a good answer, which means because both are same. So that's how we can simply do. We can simply sort it down and we can simply maintain it while comparing, okay, nums of I, it should be not equal to nums of I minus 1. If it is, please skip it, go on to the next I and simply solve it. So we'll use the exact same code which you saw above. The only part is here we did a sorting. Please remember that above the sorting is not required at all. Here we have to sort it because we need to compare the duplicates. Now coming back to the main function, which is the backtrack function, exactly same as we saw above, exactly same, because we need all such subsets we need to push in our answer. So I'll just push in all the subsets which I am making, but while making a subset, I'll make sure that I am making that subset as correct subset. So I'll just push in all the subsets. So that is for this reason. Now again, we will just simply have from start up till the end, but here the if condition will apply. How? Simply checking my nums of I should be, if it is equal to nums of I minus 1, which means if both the elements are same, please simply continue, because you can't simply push in that particular nums of I in your temp list, because for sure in the temp list, if I have pushed nums of I, right, nums of I, and now for the next number, because okay, my temp list was earlier a 1, I pushed in a small 2, because for sure at that moment it was not equal. So if it was not equal, so I just pushed in. But for the next time, again a big 2 came in picture. Now nums of I and nums of I minus 1 both are same. So simply continue, which means simply don't push this 2 now in your particular temp list. But next time when the I goes, it goes to 3. Now okay, 3 and 2 are different, for sure I can just push in my 3. So I just push in my 3 in my particular temp list, which is right now of 1. So that's how you can simply see, okay, you just simply popped it as we saw above. You can simply push it as we saw above. Simply a backtrack function. The only part is the if condition changed to not have duplicates in our entire stuff. And that's how you can simply get this stuff done by simply make sure that, okay, you are just removing, okay, as soon as you get the duplicates, you are just simply doing a continue for you. And for sure, I just to make sure, okay, you are not going beyond the actual index which you want. That is for subset 2, right? Now, going on to the next question. See, that is every problem is more or less same. Everything is same. You will see everything is same. Just a slight modification in the backtrack function. That's it. Cool. Moving on to the next question. We have an array nums of distinct integers. Return all the possible permutations. Again, all the possible permutations. You can return the answer in any order. Again, the same questions as we saw there. It is just a 1, 2, 3. Now, I just have to give back all such possible permutations, which means if I have a 1, 2, and 3, again, at the first place, my 1 can come, my 2 can come, my 3 can come. As my 1 came in, next place, I will just simply have a 2 can come. Again, okay, a 2 can come. What if a 3 can come, right? So 2 and 3. Let's say write this. Write like this, right? So again, after 2, a 3 can come. After 3, a 2 can come. So basically, I'm just concerned about the permutations. And please make sure that, okay, all the elements are distinct integers, which means I might say, okay, if it had not been distinct, it would have been a 1, 2, 2, 3. So a 1, 2, and let's say a big 2, 3. So a 1 small 2 big 2 3 and a 1 big 2 small 2 3, both are same permutations. So here also I'm not concerned about this stuff because I know, okay, all the elements are distinct. So that big stuff, small stuff would not hamper me at all. Cool. Coming back to what I have to do. Shall I return all such permutations? Which means, shall I return all such subsets? No, I cannot. While I make my particular subset, let's say I have made 1, 2. I want a permutation is it should be exactly of length 3 and should have all the elements which I had previously in my particular input. It is of length 2. Hold on. If it is of length 2, you cannot push it in your answer. It should be of length 3 to actually push it in your answer. So what you will do is, you will just make sure before actually pushing that in your answer, you will make sure, okay, it is actually of length 3. It is one such condition, one such modification you need to have in your code. You need to make sure, okay, it is of a length 3 and then you are only pushing it in your answer. Because you know that in your code, you actually keep on building by adding elements in your temp list, right? So if you are adding an element in your temp list, so please make sure that temp list length is actually what is the required length, right? So that's only you can actually push that temp list in your actual answer. So that's the reason I just make sure before pushing in, please, the size should be same. And the remaining part will more or less remain same. How? If we see that is a final answer. Now, here you see I have used a used array, which will show me, because you know one thing, as for this building of the entire stuff 1, 2, and 3, what you have to do is after 1, I just went on to 3, but then I went on to 2 back, which means I am not going linearly straight. As I was doing I+1 and the above question, I am not going linearly straight. Oh, I am coming back, which means I took a 1. I have, let's say, input 1, 2, and 3, and 4. I took a 1 in my temp list. Let's say, cool. I took a 3 in my temp list. Then I can again take a 2. But please make sure I cannot take a 1. I cannot take a 1 because it's a permutation, which means every element should be in this particular answer itself. I cannot have a 1, 1 because for sure my input was having only one single 1. So I need to make sure, okay, what all elements are used so that I will not take those elements to push it in my temporary list. So I'll know, okay, I will push it to, and for sure, by the building of example itself, you know that you have to go back to the very beginning, right? Because you have to take every such element. So I'll just simply go back and take my 2 itself. I'll start from here itself, but then it will say, for this temp list, this 1 is already used. Although you can maintain a hash set here itself, but still it's better to keep a track, okay, what is being used. Although again, I'm saying you can maintain a hash set, unordered map, anything whatsoever you want, so as to know, okay, what element you have taken already, because you cannot take that element at all. Cool. I will have this one. I'll just grab this one out. Okay. Oh, it's already used. Cool. I'll have it too. Oh, it's not used. So I can just simply place this 2 down. Okay, cool. Then again, okay, if it was my temporary list, I'll just place a 2 down, then I'll ask my recursion, please go and bring for all the possibilities. But I know it is my temporary list. I know I will just simply remove it. Okay, I'll just simply remove it. But also make sure if you remove it, you are making, okay, now it is no more used. So basically, I just keep a track of used stuff. Okay, used of 2 is actually a 1, which means, okay, I have used a 2. I'll simply call and push this element in my temporary list. So in my temporary list, I'll just push in my 2. Okay, I just pushed in my 2. Now I'll simply ask my recursive function, let's say backtrack function. Oh, your backtrack function, can you please bring me the answer? Cool, it will bring me the answer. But now I know that, okay, I have to remove this. So I'll just simply remove this from my temporary list. I'll simply remove the last element whatsoever I had. But also make sure, because you know that you push in 2 as a last element. So please also make sure that, okay, you're making your last element as used as false. Because you know, after 2, because for sure, you know, after 1, 3, I can encounter 4. So I can just push in a 4 here after my temporary list. So you know, right now 4 is there. The 2 is no more there. So simply use this 0 for 2. 2 is no more used. So that's how you can simply do a modification in your code to just simply say, okay, because earlier what you were doing, simply pushing it, simply popping, and simply calling a backtrack function. Now you know, okay, you have to also make track of use, because you know that you can go very back. After 3, I can just go very back to 2 itself, right? So I can simply use that. Same stuff as we saw here. As we saw, the condition here will change according to, because we know the temporary list size, it should be equal to the num size. So I can only push it in my list, which is the final answer. I can only push it when actually the size is same. So that is one condition which is modified. Now, coming back to the actual conditions, as you saw here, earlier I was going on from start to end, but here I'm going on from 0 to end. You know why? Because I can simply take the previous element as well. I'll take the simple previous element. Now, again, if I am taking a simple previous element, let's say I am at 1, let's say I have simple input 1, 2, 3, 4. I have the temporary list as 1, 3. I am at 1. Can I push it to 1 in my temporary list? No, I cannot. So basically, H is asked, okay, if the use of that particular element of the or that index is basically used, so please continue. So if it is used, I'll continue, which means I'll go on to the next type. Cool. Now, if it is not used, so I will simply make the use as true. Now, I'll just push that element in my temporary list. Okay, I'll just push in a 2, and then I'll just simply call the backtrack function to get in all the possibilities after this 2. Now, when this is done, which means when this is done, okay, cool, it is done entirely. I'll simply have to remove it. So I'll just simply remove it down, which means that 2 is gone. I'll simply remove it down. But as I removed it, I also have to make sure that, okay, I have to make the use of that particular element or the index. Element index you can take anyways, because for sure index is just saying, okay, unique identity of that particular element. So index taken, element taken, both are same. So for sure, but before popping, please make sure, okay, your use is actually a false, because you know that you have removed it. Now it is no more being used. And simply as it goes on to the for loop, again, it will just go on and encounter a 3. Again, 3 is already taken, so it will just again continue. Cool. If I again continue, my I will be here. Now my I will be adding to this list, and then again it will go on and find for all the permutations. And that's how you can simply modify your code. That's how that's the reason. Never ever build the entire recursion tree, or try to even think of building the entire recursion tree. Take a very start, take how actually it will actually be impacting at the mid of the problem. And that's how you can simply solve it. Going on to question number 4, permutations 2. Again, nothing a big modifications, same as we saw in the subsets 2. It's just that it can have duplicates. For sure, the issues of duplicates, simply as we saw above, simply we will just sort it down so as to make sure that, okay, we are not taking duplicates, and the same stuff if it is equal, and for sure it should not be used. because for sure if it is used, then there is no point on that. So if it is equal, it is the same condition. If it is used, simply skip it. But for sure, as we saw above also, that we just maintain, okay, the index should be actually there to actually go and have a look at it. And for sure, if it is actually same, simply continue, because I cannot take duplicates. I cannot take duplicates. So please continue if it is actually a same stuff or not. Right? And that's how everything will exactly remain same. Everything is exactly the same. Right? Exactly the same. Exactly the same. The code is down below. Now coming back to the next question, combinations. Again, it is a question asked yesterday, right? That's the reason I just building the entire playlist. It can go up to more than 1 hour, but still I want the entire backtracking playlist with you guys for to have everything. Again, in this problem, it was again a very simple one. You have an integer n, you have an integer k. Return all the possible combinations of k numbers chosen from the range 1 to n. So for this n, I know, okay, I will have a integers 1 2 3 4 5 up till n. Let's say my n is 4. Now let's say n, I have, when I mean my k's, I just can choose k numbers out of these n numbers, which means this k will define me the size. As in the beginning you saw, I have a condition on size, right? That okay, if the size is this, then only push this in your list, final list. So this k will actually define me the size. Oh, I have reached this size, so please push it in your answer. After this size, you cannot go ahead. But yeah, if you have reached this size, please push that in your answer. So this k is for the size part of my recursive function. The return part, okay, it is for my size. And still, I have to go and find all such possible combinations. Or basically saying I have to go and find all the possible combinations. Again, the same stuff will happen. I will start with 1, I will start with 2, which means I have every starting point. Now, let's say my temporary list is having a 1. I'll simply go and ask, bro, can I have a 2 with you? Okay, in my temporary list, I can just push in a 2. Next, I'll just simply go and have a 2, and then I'll ask and for all such combinations after 2. But okay, let's say my k is, let's say 3. So again, it will just go and have all the combinations after 2. But let's say, okay, it is done. It will just simply pop it down. It will simply push in a 3. So basically my start will be here, my end will be here, and then it will try on for every possibilities after this particular one. It's just that the k will just make me sure, okay, as soon as the size reaches k of this temporary list, please push that in your answer. And that's the only modification you need to have of the above problems. Cool. If we just quickly have a look, again, the same stuff. It is the final list. It is a temporary list. And for sure, I'll simply go and have a look. Now, Aryan, why 1? Because you have to start from 1, because it is from 1 to n. It is from 1 to n, right? It is not the indexing. It is actually given just the number n, just to make sure, okay, it is from 1 to n, which you have to keep track. Although you can build the entire array and stuff, but it is the elements just 1 to n, and that's pretty much it. So I just know, okay, I have to start from 1 itself. Earlier I have started from the index 0 and stuff, but no worries, here I will start from the element 1 itself. Now, very basic, the condition, I know how my k is being used. My k is only being used just to make sure my temporary list size, if it is equal to k, just push that particular temporary list in your actual list, which is the final answer. Now, okay, when it is done, simply as we saw above, I'll simply go on from start to a particular end. End is actually my n itself, because I know my n is 4. So I know if I've taken my temporary list as 1, so I will go from start to basically end. End is actually n itself, right? So I'll just simply know, okay, I'll just simply go on from start to end. For sure, I'll just push in my element I, because here index element both are same, because I am going from 1 to n. Let's imagine you make an array from 1 to n of 1 based indexing. Same stuff. So I'll just push in the element I in my index. I'll just go and find for all such permutation or all such combinations, and then for sure I'll just remove it back. And that's how you can you saw exactly the same stuff while you were doing the above problems. And that's the reason I just showed you. It's a beauty that everything just seems so seamless and is so equal to each other, right? And see, that's nothing what we did. It is the sense of what we are doing. Okay, we have a temporary list as 1. We have a temporary list as 1, starting with 2. Okay, I have a 2. I just push in. I just ask the recursive function to bring me the remaining such combinations. Then I just, okay, when it is done, I still have a 2 in my temporary list, right? Okay, I have a 2. Please remove it, because next time my 3 will come in picture. Okay, my 3 will come in picture. and that's how you can simply solve it down, right? Cool. But this you can simply solve it down. Again, going on to the next question. Combinations, sum, 3. Just more or less the same question. Is just say, okay, I have a distinct integer. Please make sure, okay, you have distinct integer, right? So no sorting and stuff would be required. Now, candidates and a target integer called target. Now, I have to return the list of unique combinations. Although I have seen the combination above, but yeah, I have to return the list of unique combinations of candidates where the chosen numbers sum to target. Now, the condition, although you saw above, I was returning the combinations of size k, right? Of size k. Here, the condition is that the combinations, it is not required to be of any size. It should be that the sum should be equal to target. So that starting if condition of recursion, that is slightly changed. Rather than keeping track of the size, I have to keep track. Okay, size is something, okay, I can just bring in from the template itself, but I have to primarily keep track of the sum of the entire particular temporary list, because as soon as the sums becomes equal to this target, I need to push in my final answer. So it is the only change. What we have to do is we have to keep track of the sum. So what I will do is in the question itself, I will just simply keep track. Okay, it is a final list which I want. It is a temporary list. It is the 2 inputs which I want, and there's one more argument we have for the start. But please make sure, please make sure that you have your something as, let's say, whatsoever is remaining, which means either you can keep track of the sum or you can keep a track of what is remaining, right? You can keep track of the sum or you can keep a track of what is remaining. Now, for sure, initially I just pushed in my target, so remaining is my target itself, because I'm just what I can do. Either you can keep track of sum and you can keep tracking element and keep adding the sum to that particular stuff. Your sum is initially a 0, and then you can simply add in, okay, any element you encounter a 1, you added a 1, so the sum became a 1, and then you added a 2, so your sum became a 3. You can keep that, or what you can do is you can have your target, and then you can keep subtracting, and as soon as your remaining becomes a 0, which means you have found a sum which is actually equal to your target. So let's see if I have an element 1, so my sum, which means my remaining will become a 6. I encounter element 2, my remaining will become a 4, and by this my remaining will keep on decreasing, and as it exactly brings down to 0, I have found these such numbers whose sum is exactly equal to my target. So that's the reason. And see, why I am focusing on taking the remaining part and not the sum part is because of the reason that it might happen that, okay, in this problem it will not hamper you at all, but in the future, let's say if you're solving a problem of DP and stuff, please make sure that it's highly recommended to take the remaining rather than the sum. Why is that the case? Because it can happen, okay, you are doing a 1 plus 2 plus 3 and so on and so forth. Now you are doing a DP, which means for sure you will be keeping track of this particular sum as well. Now, although you will put a if condition at the above, okay, if it just goes beyond, then please don't encounter and come in my actual recursive function so as to actually go and memorize or basically even check for the DP part. But if you are not doing that, then if the sum it becomes very much large, then it might give you out of bounds error. So that you have to handle it separately by adding another if condition in your DP function. But just make sure, okay, you can take anything sum or even remaining, but make sure, okay, if you're taking a sum or even remaining, please make sure that you have a if condition that, okay, if it goes out of bound, which means if the sum is going beyond your target, that you please stop right there, right? Or if the remaining is going less than 0, please stop right there, right? The same stuff we will do. We have a remaining with us, which will actually make sure, okay, we are keep track of what is remaining. And as we saw, we will make sure, okay, if the remaining goes less than 0, please stop right there and return back, else you will just go on. And for sure, if the remaining is actually exactly 0, which means, okay, my temporary list has a sum of elements which is exactly equal to my target, and that's how I can actually push that in my final list, which is the answer. Cool. Now, okay, if it is done, everything is done, I'll simply know, as we saw in the above, we are simply going on all such from start to end. Again, the same stuff, again, exactly the same stuff. It's just as a condition. This condition changed, and it should be now equal to the sum called as target. Again, everything remains same. I'll go on from start up till end. I'll just push on this particular element. I'll just go and have a recursive function call with the remaining sum, because if I've taken this particular element in my nums, in my temporary list, so for sure the sum will actually reduce. So that's the reason. If my sum, it actually is reducing, please make sure that, okay, you are actually reducing the sum as well, so as to get it element. And for sure, go and try for the next element. But here a good thing which you will see is that you can take an element any number of times, which means earlier you saw one thing. If I have taken a 1, I have taken a 2, I was taking 2 only once, and I was doing a I plus 1 to take the next element, which is 3. I know the elements are distinct for sure, but I can take a 2 again, which means if I have taken a 2, it is not necessarily that I will go on and take a 3 next. I can again go and take a 2, which means if because earlier what we were doing is that we cannot take any element as many times as we want. So what we are doing is, if we have taken an I, we're going to simply I plus 1. But here what we saw is, okay, I have taken an I can take the same element 2 again. As you saw here also, I have only 1 2, but still I have taken the 2 again. I can take the same 2 again. So what I will do is I can take the same 2 again. So now my I, rather than going to I plus 1, it will again switch back to I, so as to get the same element again. So just changing, I plus 1 is now still back to I, because I know I can take the same element again. Now Aryan, what if it just goes infinite times? No, it will not, because even if you keep adding the same element again, how many times you will add? At max, okay, it's just saying at max you will add, okay, such that the sum becomes either less than 0 or the sum will actually become equal to my target. And for sure the elements are not that even big that you can actually keep on adding it and it will not be even becoming equal to your target. Right, even if you add 2, maximum 20 times you can add that, it will exceed your target. So it will at max go to up till 20 times. So that is very much easy, that okay, you can simply go and have it from I itself, because you know you cannot go with I plus 1, because you can for sure take the same element as many times as you want. That's a slight modification, and see, you would see that okay, every code is looking more or less same. It's just a slight modification in the code itself. That's it. Again, going on to the next question. Combination sum 2, again exactly same. It's just that we are having a collection of candidates and a target number. Find all the unique combinations in the candidates where the candidates sum equal target. Now the again same part, it is not saying anything about the distinctness of the element, which means I can have same elements as well in the input. Earlier what we saw, we are having distinct elements, and for sure you know that while not to counter the same stuff twice, we just simply make sure that okay, we just sort the stuff down, and please make sure that okay, you are maintaining that order, that I should just maintain that if both the elements, which means nums of I is equal to nums of I minus 1, please continue, because you cannot take the same stuff twice, which means one small 2 and one big 2 both are same. So that's the reason, as we have seen it 3 times earlier also, just a one small condition and the remaining part is exactly the same, right? Going on to the next question. Again, it's just to show that okay, it's a question of recursion and not the backtracking. How you will see it, that okay, you are having a string containing of digits from 2 to 9 inclusive. Okay, cool. It's just a number pad which you have in your Nokia phone. If you don't have it, you are not the good child. You should have a Nokia phone with you, right? Return all the possible letters combinations that the number could be represented, and return the answer in any order. Right now, okay, I just type in a number, let's say 2. So basically, if I type in 2, I can type in a A, B, or C. If I type in a 8, I can type in a T, U, and F, right? So it can be anything. So that's the reason I'm mapping. It just says okay, if you have a number 2, so you know you can start off with A or a B or a C, or a B, A, right, or a B or a C, right? And then if I type in a number 3, I can have a D, E, or F after a A. That is a part that okay, for this 2, I have my recursion made as A, B, and C. After this A, B, and C, I will have a D, E, and F. D, E, and F. D, E, and F. It is not backtracking, which means it is not that okay. I was having it is not that okay. I was having a 1, 2, and 3, or let's say a simply 2 and 3. Let's say simply 1, 2, and 3. It is not saying okay, you can have a 1, 2, and then a 1, 3, 2, or maybe a 1, 2, 3, or maybe I have to remove and bring a 1, 3. It's just saying after every element keep on adding, which means after 1 comes a 2, after 2 comes a 3. So basically after 1 all the possibilities will come in, that okay, your 2 will add in, after 2 all the possibilities will come in, which will add a 3. So that's a simple recursion being made. No backtracking is required at all in this. So the code, as you saw above, you will have some of the answers and stuff to just put in your answer. It's just that you will see in your code you are just simply calling one recursive call. There is nothing, while coming back, there is nothing being changed, because you know after you have a 2, let's say here itself, after you have a 1, you have all the possible stuff of 1. Like when I say 1, I mean actually let's say A, B, and C. So it's just a starting point. After I'll simply push in the 3 stuff for particular 2, and for again a 3, every 3 stuff will come in. So that's a simple recursion being punched in, that okay, you have a combination, you will have another letter which will just being pushed in, and for sure I'm just going forward and I don't want to come back to just change any of the previous element I pushed in, because I'm just going in order itself, and I just won't want to go the entire tree without actually going on and coming back to actually change any of the previous numbers. Which means once I've got a A, it's good for me. It's just that okay, I'll just try on for every possibility of the input itself. Okay, I'll just try for A, B, C. Cool. When it is done, I'll simply go and try for a D. Although people might say, okay, Aryan, you added a, then you added a D, then maybe you removed a D and then you added a C. That's also you can do, but it is not required, as if, because as you are keep on building it, and you just want everything out from this particular entire tree itself, right? So even if you have a temporary list with you, let's say a string, you can actually build it. Okay, what I will do is I will simply take in a, I'll simply have a D, and then maybe I'll remove a D, I'll have a C, then I'll remove a C, I'll have a E, then I'll have a F, but then I'll say okay, remove the everything as well, and then keep on doing it. Although you can just make the question like this as well, but that can be simply solved by recursion, because you don't need to come back. Is a string you need to maintain at every point. It is not that okay, I have a big vector, I can't go beyond that particular stuff, I can't take the vector. In the actual questions of backtracking, if you just keep on maintaining the vector at every point of time, that's also good, but you cannot, right? So you have to just use the same vector again and again. Here you will see that, and for sure that can be for sure solved by iterative versions. Every question can be solved by iterative as well. That's a simple reason that okay, we are just taking the temporary as a string and not the address. If we had taken as the address, we could have solved it via the backtracking as well. But as we know that it is not that great, not that big, so we can have in all the possibilities and that won't go big. But if you want to solve it via backtracking, you can solve it. Take this temporary as an address, and while coming back you can just remove that digit and can push that digit. That's how you can know by simple stuff that okay, if I can just bring out every part, I can bring in. If not, then I can just simply go and try for a possibilities, and I can come back and remove the possibilities from here. Again. That can be solved by simple backtracking also, and a recursion also. Why recursion simple? Because the size is pretty small, so the copies made won't be that large and big. But in a simple recursion code, if you don't do a backtracking, it will keep on making the entire copies, and that entire copies will take so much of space and time that it would be actually getting time limit exceeded. That's the reason we actually go via the backtracking path. Okay, I added a D, I have made all the possibilities, and then when I'm coming back, I can actually remove this D and add a E after my A. But still, here I can simply solve this via recursion as well, because it's a simple temp, and that's the reason. Keep thinking every problem as a recursion, backtracking, and an iterative as well. Iterative we have seen quite a lot. That's the reason we are not pushing it that in this video. But yeah, That is one such method to actually think of any problem. Now, coming back, and again, I'm saying that can be solved by a simple backtracking as well, but simply it's easy to actually just push in two conditions here and here, push in that element, which means this letter, push that in temp, put in here, remove that element from the temp, add it here. Simply go via that route as well, but there is not any such good way to actually add an element inside a string and then remove that element. That will still take that O of n time, which we want. But yeah, because in a vector, pushing an element is just O of 1, popping an element is again a O of 1. So that is a O of 1 operation. But yeah, here just adding an element and removing an element will again be O of n operation. So that's the reason more or less it will remain same even if you just do a backtrack or a recursive. But if it had been a vector, the recursive would have been the best, but it's a string of small size. So that's the reason our actual recursive is also good, as equivalent as backtrack one. Now, some of the practice questions for you to practice are down here for your practice. N queens one we will see, because for sure let's have a hard question also. And see, again, it will be more or less same as we have seen above. Still, I just highly recommend go and practice these questions for sure. Going on to the n queens problem, it just says, okay, you have n queens puzzles, which means you have an n cross n chessboard, and you have to place n queens inside the chessboard such that for sure you have to go on and print all the distinct solutions, right? And for sure make sure that no queens are attacking each other. No two queens are attacking each other. And okay, each solution, how we have to represent is, for the empty spaces it's just a dot, for the queen is just a q. Empty space dot, empty space dot, empty space dot, queens is a q. That's how I can actually build my answer. Now for sure it can be possibilities that, okay, I have just made the entire board myself, and let's say I have built the entire board and the queens are placed very well here. Now I have to place another queen. Let's say the board is extended here and the board is extended here. So now let's say I have to place another queen, so I can just place that queen here maybe, and then I can use that same stuff to place another queen, let's say here. Let's say here. So that's how I can simply solve my recursion. Okay, I can use the same sub problem, and I can use that sub problem to actually try in for every new possibilities. Same as we saw above, that okay, I have a B, let's say I have a 1 2 3 4, and I want to build on all such combinations or permutations, or let all such combinations. So I just have a 1 2 with me. Let's say I have a 1 2 with me. Now I will add I'll try to for a 3, I'll try to have for a 4. Now after, let's say I have a 5 also. Now after 3 I will just try on for every possibilities. Again I'll just remove 3 and I have 4 and try for all the possibilities. That's how I can simply have a small subset of my chessboard ready, having good queens. Again the same, having good queens. Now I'll just try to place one queen at some location, let's say 3, let's say the third row. I'll try to place my queen at, let's say the third row. I am placing the queen at the third column. Here I'm placing the third queen at the third row. I'm placing the next queen at the fourth column. So again I'm just going and trying on for all the possibilities for all the remaining such rows. Okay, if it is possible to actually place in the queen as well. And that's how you can simply relate it, that okay, you are just having everything ready and you are using that ready everything. It is ready. 1 2 is good. Now you're just trying to place queen in, let's say, the next column or next row, whatsoever you want. Here we will see, okay, we will just trying to place a queen in next. I'll also show you. We are just trying to place the queen in next of the columns, right? And when I say I'm trying to place a queen, I have to make sure that okay, it should not be attacking any other queen placed so far. So I have to also make sure I have to maintain what all queens have been placed so far. As you remember that we were maintaining, as you remember that we were in the above questions, right? Permutations and stuff. We were maintaining, where is that question gone? Right. If you remember, we were maintaining, okay, if it has been used or not, because we know if that location has been used, you can't use that location. Here itself, it is just that, okay, if that queen is placed here, I need to make sure, okay, what's the location of that queen such that I know I can't go on that location. I have to make sure, okay, my queen should not attack that location at all. Now, again, the same stuff, we will have a result to keep the final result of all such n queens combinations. We will also have my n queens. As you having your temporary list, you will have the n queens. Initially, just simply all dots, no queens placed so far. Now I'll just go and start off with my final list, my actual queens, my n is the size, and my n is the row, because I'm starting from the row, because you know, I just need to have a start. As I mentioned in the very beginning, I need to have a start. Now start can be an index, it can be a row, it can be a column, it can be anything, right? As you saw in one of such questions of combinations, it was a number. Start was a number, just a 1, right? That's how your start can change itself entirely. Now, okay, I have my start as my row. I'll simply go on and see, okay, if actually, just to say, if my row is n, which means I have reached the end. For sure, because you know, you have to have the entire n cross n filled with queens, filled with n queens, and for sure at every row, just one queen can come. So for sure, if I have reached n, and Aryan, what if the queens which you have made is not good? No, I will make the queens sit only such that they are good. Only then I can actually place in my, I can actually reach my row n. I'll always try to place in good queens only. Right? Like when I say I'm trying to placing good queens, I mean I'm placing a queen at its correct location. So I just say, okay, if the row is n, please push in that n queens with you, which is the n queens is the temporary list which we have made so far, and simply return. Now, if not, then for that particular row, I will try on for all the columns, right? So as you were seeing that, okay, in your recursive call, you were trying on for all such possibilities, right? So for that particular row, I'll try on for all the columns. For that row, I try on for all such columns. Now, when I say I try on, I'll just say, okay, placing that at that particular row and column, if I am gonna place a queen consisting of this temporary list, which means this list, which is n queens, is the list made so far. It is the list made so far. If I have, okay, it is the n queens placed so far. Now I am going and placing my new queen on this row and column. Is it a valid? Now when I say it is a valid, I need to make sure, let's see if I am placing at this location. Now I need to make sure, okay, this stuff and this stuff is not there. Now for sure, the row part, I am already placing in the next row. So row stuff, I don't need to check because I'm already placing the next row itself. So row part will already be sorted, but this part, that no one should be at its column, I need to check that. No one should be diagonally like this to him, and no one should be diagonally like this to him. These are three things I have to check, right? So that's what I will do in is valid function, which will check remaining queens placed are they here at n queens. I am going to place at row comma column, so please make sure, okay, it is valid. It will go and check for the entire column, for the entire diagonal, which is the 45 degree, and the entire diagonal, which is the 135 degree. So I just check for the entire column, which is the above column, from I to actually row, which means I equal to 0 to row minus 1, because I know I'm placing at row itself. So it is for the entire column which I'm gonna check, right? How you say for this particular row, for this particular R comma C, you just go on to every row to get, okay, for this the coordinates are R comma this particular row, which is, let's say I am just going on, my I is going on from 0 to row minus 1, right? Row minus 1. So I just go on that the coordinate is R comma I, where I is going from 0 to row minus 1, right? That's the reason I just go on from I to column, which means here I am fixing my particular column. So okay, my column is fixed. Now I am going on to every such row. My column is fixed. I'm going on to every such row. Let's say here my column is fixed. I am going on to every such row, which is this row, this row, this row, right? So for sure here I am going at all such rows, because here you saw the row is changing, the column is fixed. So the column is fixed, which is the column, and the row is changing, which is I for row minus 1. So I comma column. That's a bit, I just change it, but yeah, I am going on for every row from 0 to row -1. So it is I comma column, right? So I just go and check for I comma column. If it is actually a queue, I cannot place my another queue at this location, which is this particular location. I cannot place another queue. So please return a false. But if it is not, then simply go and check for the 45-degree diagonal. Simply going and checking for all the locations which are here, and I'll just again make sure, okay, if it is a queen at that location in the diagonal, and please make sure if you want to reach, please choose a starting location which is I comma j, and keep on doing I minus minus and j minus minus to actually going like this down, right? And again, for you have to go and check for 135-degree. You can just go and see for I minus minus and j plus plus to actually go and see the 135-degree down. That's how. If everything is, if anything is at moment having a queue at that location already, please return a false, else simply return a true. Now when it is done, when I know, okay, placing a queen is bad at that location, I will simply go and place a queen in that location, and also will go and ask my recursive function, please go and try for the next row to place a queen. But when my recursive function has gone and try for everything out, then I'll just simply place a dot back, which means I'll remove the queen back from that location so that it can actually go and try on for other possibilities to actually place the queen at the next columns. Because for that row, I have for that row, I have placed my queen at that column, but for that row, I will try on for other columns as well to place a queen at that location. And that's how you can simply solve this problem of backtracking of n queens. It's actually a hard question, but yeah, we have seen so much. Okay, we know the standard stuff is just trying to place it, asking recursion to bring in the answer for next one, and just removing it back, and then again asking the recursion. Sorry, and then removing back, and then the loop will go on, trying for all the possibilities. And that's how that was a complete guide for backtracking for you guys. I hope that you guys enjoyed it. If yes, then do smash the like button. It has motivated a lot. See you in another one. Goodbye, take care. Bye bye. Please like it. Bye bye.